You've heard a little bit about Sam's talk and David Jones's and Patrick Aleo's talks, but now you'll hear from the man himself. So Sam, please take it away.
Yes, great. Can you see my slides? You can hear me okay?
We can hear you clearly. Yeah. Please go ahead.
Awesome. Okay, so hi folks, thanks very much to the organisers for setting this up. The talks this week have been really great. So my name's Sam, I'm a second year PhD student at the Institute of Astronomy, University of Cambridge. I work with Case Mandel, Stephen Thorpe, Zahil Dewan, and many different international collaborators as part of the Young Supernova experiment. So today I'm going to be telling you about a BayeSN analysis of Type 1a supernova siblings and prospects with the VRC Rubin Observatory. So this is a talk about supernovae which go off in the same host galaxy, and when this happens we refer to the supernovae as supernova siblings. So the first part of this talk is going to be a general overview of Type 1a supernovae and systematics. I'll then describe why siblings are useful. The third part of this talk is going to be a summary of the analysis we've been doing for the past year, looking at siblings using a Type 1a supernova model called BayeSN. And finally, I'll discuss the things that we can do with siblings that will be discovered and observed as part of the legacy survey of space and time. Type 1a supernovae and systematics. So as we're well aware, Type 1a supernovae are stellar explosions, and we can treat them as being standardizable candles. We can correct for population correlations with the light curve shape and apparent color and standardize the absolute magnitudes. Coupled with a measurement of apparent magnitudes, we get an estimate of luminosity distance, and couple this with an estimate of cosmological redshift, and we get a Hubble diagram from which we can constrain our cosmological parameters of interest. And the goal in the years ahead is to control for the systematic uncertainties, which will dominate our estimates of distance and hence our cosmological parameters. So what are the key systematics which we're looking to understand and control for in the years ahead? So a big open question at the moment is, okay, how is the supernova population correlated with the host galaxy properties? The most notable empirical finding is the mass step. This says that Type 1a supernovae in host galaxies with a high stellar mass appear to be optically brighter, whereas those in lower stellar masses appear to be dimmer. So the question is, why is this the case? And what is the astrophysics that's driving it? Is mass the direct tracer, or is it a weak tracer? Are the local host galaxy properties more important, things like the star formation rate and the metallicity? And understanding the astrophysics here is really important because galaxies evolve as a function of redshift. So if there's some astrophysical tie there, then so too the supernova population may evolve. So to avoid biasing our distance estimates at high redshift, we really need to understand the astrophysics here. In turn, we want to be looking at correlations between the intrinsic supernova population and the host properties, but this is a difficult thing to do because it requires accurately estimating the dust. So the cutting edge at the moment is, okay, perhaps the mass step is explained away by different intrinsic populations in different host environments, or on the other hand, you could have different dust distributions in different host environments, or it could be a combination of these effects. So these are the key systematics which we're looking to understand and control for in the years ahead. So how is it that Type 1a supernova siblings can help us in answering some of these questions? So supernova siblings all occur in the same host galaxy, so they're all at the same distance. They share some common host galaxy properties, so they certainly share their global host galaxy properties, things like the host galaxy stellar mass. And a more subtle point is that they share the siblings' mean local host galaxy properties. So the siblings' mean star formation rate, the siblings' mean metallicity, things like this. They also share the same peculiar velocity and the same redshift as well. So what this means is there's no variation of these common properties, which contributes towards an intrinsic scatter of siblings' distance estimates relative to one another. So if you've got individual distance estimates, one to each sibling, they have some intrinsic scatter, and there's no contribution towards this intrinsic scatter from a variation of these common properties. But in a population, these common properties do vary. So we expect a difference between the siblings' scatter and the total intrinsic scatter in the population. So when we're looking at the siblings' distance estimates, we're ultimately honing in on how well we're modeling the stuff that does vary. So how well are we modeling the intrinsic SEDs? How well are we modeling the dust extinction, which probably varies amongst these siblings? What is the effect of the local host galaxy properties, which varies amongst these siblings? And the big picture here is that studying the consistency of individual siblings' distance estimates is a path towards understanding the dominant contributions towards the total intrinsic scatter in your Hubble diagram. So to help visualize this, we're going to start off with a simple picture. You've got individual galaxies, each with an individual supernova. You get a photometric distance estimate to each supernova by fitting the light curves. And you also have a cosmological distance estimate from assuming a cosmology and using an input estimate of cosmological redshift. So the difference between these two is the Hubble residuals, and how well these two typically agree is characterized by the scatter in the Hubble residuals. This is the total intrinsic scatter, which in our notation is sigma naught. So if each of these supernovae has a sibling companion, they're also drawn from the same population. They also have the same total intrinsic scatter, sigma naught. But the known unknown is, okay, what is the intrinsic scatter of these siblings' distance estimates relative to one another? So this is characterized by a parameter which we're calling the relative intrinsic scatter. And if we pull the constraints across multiple siblings galaxies, we can get a posterior on this sigma rel parameter. So the cool thing about this constraint is that we don't actually need our cosmological distance estimates to constrain this parameter. We don't need to assume a cosmology to have constraining power over the relative scatter. So in this picture, I've drawn the siblings' distance estimates as being quite correlated with one another. This is equivalent to saying that the relative intrinsic scatter is small, much smaller than the total intrinsic scatter in the Hubble diagram. But it may well be the case that this relative scatter is large and comparable to the total intrinsic scatter, which is equivalent to saying that the siblings' distance estimates aren't correlated with one another. So draws from within a galaxy are the same as those drawn from a population. And which of these scenarios is closer to the truth can actually help you understand the correlations with the host. So if sigma rel is really small, the case where your siblings' distance estimates are correlated, this implies that it's the siblings' common properties, which varies in the population, that contributes most towards the total intrinsic scatter. And in turn, this begs the question, okay, what is it our siblings' distance estimates are correlated with? And can we use this information to better understand supernova host correlations and improve standardization? On the other hand, it could be the case that sigma rel is large, the uncorrelated case, in which case it's the stuff which varies within the galaxy which dominates your total intrinsic scatter. Or it could be a mix of these two effects. So I would say that there's been two sibling studies looking into constraining the siblings' intrinsic scatter across a population of siblings. The prototype study doing this was in Skolnick 2020. And in our notation, they essentially say that sigma rel is probably greater than half of the total intrinsic scatter in the Hubble diagram. A separate study in Burns 2020, looking at a different sibling sample using a different model, after they make some sample selection cuts, they find a small relative scatter value. So you've essentially got a tension between these two scenarios. And I think figuring out which of these scenarios is closer to the truth can ultimately help you better understand your supernova host correlations and in turn improve standardization. So that's the utility of type 1a supernova siblings. So the third part of this talk is a summary of the work that we've been doing for the past year, looking at type 1a supernova siblings using a model called BayeSN, and hopefully this work will be on the archive within the next couple of weeks or so. So we're part of an international collaboration called the Young Supernova Experiment, which was discussed by David Jones and Patrick Elio in their talks on Tuesday. So as a reminder, this is a 3-year transient survey, and it's discovering and observing and many different types of transients, including type 1a supernovae. And one of its goals is to build a low redshift sample of type 1a supernovae to anchor those observed at high redshift by Rubin and the Roman Space Telescope. So last year, it observed SN 2021 HPR in GRI-ZY passbands. And it turns out this is the third spectroscopically confirmed type 1a supernova in this galaxy NGC 3147, which is a high stellar mass Cepheid calibrator galaxy. So it's used in the intermediate rung of the distance ladder to constrain the Hubble constant. And this was the initial motivation for looking at these siblings, saying, okay, can we constrain the Hubble constant? And what is the effect of, instead of having just one supernova in this galaxy, we've got 3. So this is the trio of type 1a supernova siblings in NGC 3147. We've got 21 HPR, 08 FV, and 97 BQ. So we fit these siblings light curves with BayeSN. So BayeSN is a hierarchical Bayesian model of the type 1a supernova spectral energy distributions, which has been developed by Stephen Thorpe and Casey Mandel in the group here in Cambridge. So Stephen discussed this model on Tuesday, but as a reminder, a quick summary of this model is that it models 2 distinct distributions, one of the intrinsic SEDs and one of the dust. And we train this model on both optical and near-infrared light curves. So near-infrared light curves are doubly advantageous Firstly, because these photons are less sensitive to dust as compared to the optical. And secondly, because the population dispersion of SN1A luminosities at near-infrared wavelengths is relatively small, even without standardization corrections. So given this double advantage and this hierarchical Bayesian setting, you ultimately get a better constraint on the dust and hence the intrinsic SEDs, so this trains up your model, which you can then go on to apply to new supernova light curves, which you haven't seen before. So the key parameters to be aware of that we have constraining power over when we're fitting a supernova's light curves are the dust extinction AV, which is the amount of dust, and the dust loss shape RV. It parameterizes extinction as a function of wavelength. We also have the light curve shape parameter theta. This is the coefficient on the first functional principal component, but intuitively this is just the light curve shape, and it gives rise to well-known empirical relations like the Phillips relation that optically brighter supernovae take a longer time to decay in brightness. So this is what we're doing when we fit a supernova's light curves. We've got the dust parameters, we've got the light curve shape, we've also got some residual perturbations on top of the SED, and we've got the distance in there as well. So these combine to create latent SEDs and in turn light curves. And the power of Bayesian inference is to fit the real light curves, and you solve the inverse problem. You get a posterior on these parameters of interest. So this is what we do with our siblings. We fit each sibling one at a time, and we get 3 individual distance estimates. So the most obvious question we can ask initially is, okay, do these 3 individual distance estimates agree with one another? And the answer is yes, if we assume a value for RV, or if we allow RV to be a free parameter. In both cases, the distance estimates are consistent with one another, and the sample standard deviation is very small, actually much smaller than the total intrinsic scatter in the Hubble diagram. We also fit with Snoopy. These distance estimates are also consistent, though the sample standard deviation is a little bit larger. So in terms of drawing conclusions about model robustness and model comparison, really the rigorous way to do this is to get a posterior on the relative intrinsic scatter, the intrinsic scatter as implied by the spread of these individual distance estimates relative to one another. However, because the sample size is so small here, we don't get a tight constraint on the sigma rel parameter. So we really need to be looking at more siblings. So we extend our sample briefly in this study. We look at 4 extra galaxies with supernova siblings. There's a pair of transitional type 1a supernovae where the distance estimates disagree, but in all of the remaining cases where we've got normal type 1a supernova siblings, you can see that the distance estimates are consistent with one another. And just looking at this plot of the Hubble residuals, it seems to be closer to the case where the distance estimates are correlated with one another, which is equivalent to saying that this sigma rel is smaller than sigma naught, the total intrinsic scatter. So we get a posterior on sigma rel as implied by the normal type 1a supernova siblings. And we compare this against sigma naught, which is constrained from a separate sample, the BayeSN training sample. So this is a slight caveat with the result, but nonetheless, we estimate that there's roughly a 90% probability that sigma rel is less than sigma naught. So this aligns with our qualitative expectations, namely that the siblings' common properties probably contributes towards the total intrinsic scatter in the Hubble diagram, and hence doesn't contribute towards the relative intrinsic scatter. How much less sigma rel is compared to sigma naught can best be answered by looking at even more siblings. And then this then begs the question, okay, what is it that our siblings' distance estimates are correlated? How can we account for the fact that sigma rel is less than sigma naught? So this result is indicative, and it motivates future work to be analyzing more siblings. So we proceed with our analysis to say, okay, what happens if we give our model more information? So whereas before we were doing individual fits, what we now want to do is tell our model that these siblings are actually at the same distance. So we build a novel fitting architecture where we fit all of the siblings' data from within a single galaxy at the same time. And we have a single distance hyperparameter. We impose that they must be at the same distance. And the sharing of parameters when we're fitting the light curves is a unique capability of BayeSN. So this is the posterior we get from fitting all of the siblings' light curves in NGC 3147 simultaneously. So we have a single distance hyperparameter, but we allow things like the dust extinction and the light curve shape to be different for each sibling. How do these constraints compare to the individual fits? So if we pick an individual supernova 97BQ, the orange contours here is the individual fit to this supernova, whereas the black contours here are the posteriors on the same parameters, but where we're benefiting from the other siblings' data in the hierarchical fit. And what you can see is across all of these parameters of interest, you're getting more precise constraints. So what we can say is that, okay, just as near-infrared data gives you added leverage on the dust parameters and hence the distance, so too it seems that siblings data gives you added leverage on the distance, and this informs the remaining parameters like the dust parameters. So the big picture here is that if you've got siblings data available, you're better off hierarchically fitting this data to get better constraints on your parameters. Okay, so the culmination of this work and taking into account all the lessons we've learned along the way is to use this galaxy to constrain the Hubble constant. So we have the trio of type 1a supernova siblings, we have a Cepheid distance from Reese 21, and we have a set of Hubble flow type 1a supernovae. So we do a blind analysis. So before we unblind, we settle upon, okay, what's going to be our best model fitting configuration? What choices are we going to make? So we fit all the siblings light curves at the same time. This allows for the hierarchical sharing of information. And the entire fit is a one-step process. So we also fit simultaneously with this, the Cepheid distance and the Hubble flow type 1a supernova distances. We marginalize over all the uncertainties in the dust parameters in the calibrator galaxy. And we also marginalize over the relative intrinsic scatter in the siblings in the calibrator galaxy. And we do this by imposing an informative prior that sigma rel should be somewhere between 0 and sigma naught. This is justified by our multi-galaxy siblings analysis and also by our qualitative expectations. Something I won't get into now, but something which we show in the paper is that this marginalization ensures that your distance uncertainty is accurately quantified. So we're not being overly pessimistic or overly conservative or overly optimistic. This marginalization extracts the most information out of your siblings data.
Sam, 5 minutes.
Thank you, cheers. And the final thing we do is marginalize over the total intrinsic scatter in the Hubble diagram, as well as the peculiar velocity dispersion as well. So we unblinded this week and we've done a long MCMC fit. So this is the posterior we get on the Hubble constant 77.9 plus or minus 6.5. So this is consistent with typical local universe measurements, but it's also consistent with the early universe measurements constrained by Planck. So really the limiting factor here is the fact that we've just got a single calibrator galaxy. So with more calibrator galaxies, we can get a more accurate and precise constraint on the Hubble constant. But nonetheless, we've demonstrated here how to use siblings data effectively to extract the most information out of your siblings data wherever it's available. Okay, so what is it that we can hope to do with type 1a supernova siblings that are discovered as part of the legacy survey of space and time? So the big picture here is that we want to be constraining sigma rel and comparing this against sigma naught, which is constrained from the same sibling sample. This tells you whether it's, okay, the sibling's common properties or the stuff which varies within the galaxy that dominates the total intrinsic scatter. And this can improve your understanding of SN host correlations and improve your standardization in general. I think a cool thing to do would be to compare sigma rel in different host property bins. So what is sigma rel in high stellar mass host galaxies? How does this compare to that constrained in low stellar mass host galaxies? So Skolnick 2020 estimate that there's going to be around 800 galaxies with type 1a supernova sibling pairs by the end of the 10-year legacy survey of space and time. And it's worth noting that in addition to these, you'll also have the LSST supernovae. You can pair these up with archival non-LSST supernovae to create a sibling pair. So the number of galaxies here is probably going to be larger than this. So a question I'm looking to answer with some preliminary work is, okay, how many siblings do we actually need to tightly constrain this sigma rel parameter? So Alex Gagliano sent me some simulations based on the LSST wide fast deep survey using the Scotch tool presented in LOC in 2022. So these are some typical examples, and as you can see, the photometric cadence is fairly low. So a control set which we compare against is the foundation DR1 set of light curves. So when we look at the typical errors on distance estimates from fitting each supernova, for the foundation DR1 light curves, you can see you expect the distance errors to be less than 0.1 mag. They're all grouped here. Whereas if you fit these LSST WFD light curves, on average, you're getting a much larger error on the distance estimate. And this can be attributed to the much lower photometric cadence. So what does this imply about the posteriors you get on the relative intrinsic scatter? So first, looking at the foundation DR1 light curves, you've got some sigma rel posterior summary statistics. So these points are the medians. You've got the 68% intervals and the 95% intervals as well. And what you can see is that with more siblings galaxies, you get a tighter constraint on sigma rel. So if you stare at these plots long enough, you say, okay, with about 100 galaxies, I'll get a 68% uncertainty of about plus or minus 0.01 mag. So this allows you to compare sigma rel in different host property bins. However, for the LSST simulations, you can see that the posteriors are much larger. So with 800 galaxies, you can probably constrain sigma rel, but you're probably limited in your ability to compare sigma rel in different host property bins. So a rough conclusion from this preliminary work is the WFD cadence really only yields modest constraints on sigma rel. Future work is going to look at the deep drilling fields, which will yield a higher photometric cadence, but probably a reduced discovery rate of type 1a supernova siblings. And I think a good idea would be to prioritize supernovae that are discovered with LSST in galaxies where you already have an archival non-LSST supernova. I think this is a good way of guaranteeing that you have high cadence in both of your siblings. So in conclusion, I think the utility of siblings is characterized by the posterior you get on the relative intrinsic scatter. And comparing this against sigma naught tells you whether it's the siblings' common properties or the stuff which varies within a galaxy that dominates your total intrinsic scatter. We've built a novel fitting architecture that fits all siblings from within a single galaxy simultaneously, and we get better constraints on all of our parameters of interest. LSST is going to discover many more type 1a supernova siblings, and high cadence photometry is always going to be desirable for making the most of these. So thanks very much for listening, and I welcome any questions you have.
All right, thank you for that. So we'll take questions, and because of this talk, each speaker is allowed to ask 2 questions.
Hey, Sam, that was really cool. This is Justin Perel.
Hi there.
So this is it's a cool situation where you have sort of like a real data, but you can look in the back of the book for the distance. So I think that's like a unique situation that I think is interesting. So did you do some other tests that are not really H0 related, but checking like, okay, you have 3 supernovae and you kind of know the answer. So if you fit like different bands or only optical versus only the near infrared, I don't know, do all those situations just continue to agree with each other? Or, I just wondering if you did anything like that.
Yeah, so it's a good question. So I think we did these tests back in the day, but I think the big picture here is like, okay, you fit optical only, and what you find is, okay, perhaps the sample standard deviation is a little bit larger. But the thing is, you've always got these errors, the errors on your distance estimates, regardless of the intrinsic scatter. So really, the sample standard deviation isn't the important metric. It's the posterior you get on the relative intrinsic scatter. So so we could do these tests just for these 3 supernovae, and you say, okay, the sample standard deviation is just as small or it's a little bit larger. But ultimately, your posterior on sigma rel is still really, really wide. So if you want to actually definitively answer this, you need to have a much larger sibling sample, and we didn't do different band tests for the multi-galaxy sibling sample, but this is something that you could do with more siblings. Yeah.
This is Simon Beer. Thank you very much for a great and very clear talk. I was wondering, looking forward, can we do even more sibling studies, say, in specific regions in the galaxy, or if you have spectra of going higher order, even closer, quote unquote, siblings, that we can even learn more than just host association?
I'm not sure I completely understand the question. I guess you're saying, okay, can we look at the different host properties, so like measuring all the different stuff, and also kind of perhaps the distance from the galaxy center, and look at how this correlates with our siblings' distance estimates. Is that kind of the question?
No, just going higher order. So far you define siblings by same host. If you have more,
right.
So can you do same same region in the host, or same specific spectra, or
I see. So so you're saying looking at two or more supernovae which aren't in the same galaxy but have similar properties. I guess that's what you're saying.
Or even same galaxy, same location within the galaxy, or same galaxy and some same.
Sorry, I don't know if you cut out there, but I'm not entirely sure what the question is asking. I guess I think an answer to your question is we're making an assumption here that sigma rel is the same parameter for all of the galaxies we're looking at, and this is an assumption, and we kind of need to make this assumption to have constraining power over sigma rel in a multi-galaxy siblings analysis. But then binning this up into different host properties is something that you can do also. So the example I gave was, okay, what's sigma rel in low stellar mass host galaxies? How does this compare to that in high stellar mass host galaxies? So these are all things that we can do. But the limiting factor is, okay, we need to have enough siblings discovered, but also the light curves need to be good as well. You need to have a high cadence. So yeah, I'm sorry if I've not fully grasped what your question is asking, but yeah, we can chat about this.
Chat offline, yeah. There's another.
Yeah.
We're all good, Sam. So I see that there's pressing questions both online and in the room, but in the interest of time, I'm going to have us go on to the next speaker. Please take any other questions for Sam onto Slack.